So that's the problem, understanding what it is we're trying to do. Now I want to talk about learning and its relationship to reverse engineering and how physical systems can and can't do that, when they can do it easily and when they can't. In particular, I'm going to spend a bit of time talking about learning in neural networks as though it's stress-induced folding. So we can understand the problem of biology in mind as deep reverse engineering, that adaptation requires us to be able to do deep reverse engineering. So what's reverse engineering? Well, I give you an example of a system, something that already works, and you need to make a new system that does the same thing. For example, somebody gives you an Atari video game and you have to reverse engineer the code that makes it play the same game. Biologically, this would be, if I knew what the required changes were to a phenotype, can you tell me the genotypic changes that would do that? Or if I tell you the required changes to behavior, can you tell me the changes to the mental model that does that? Now, reverse engineering of that kind is easy when it's shallow. If I give you a leaf and I ask you, can you make something, can you reverse engineer something that creates that just in terms of its two-dimensional physical structure, you can just push it into clay and then you can make prints of leaves from that cast all day long. Or likewise, you can pour jelly into a mold or run water down a mountainside and let the mountainside deform to the path of the river. In other words, shallow reverse engineering is easy. You just push it where you want it to go. If, for example, we apply a force to the top of a complicated structure like a pylon, push the top of it to the left, then the structure accommodates or deforms to accommodate to the forcing that it's experienced. That means that all of the struts and girders in the system give way a little bit or bend a little bit, and they bend in just the right way to accommodate to that structure. How does the system know what parts to change? How do the parts know that they're the parts that are supposed to change and the other parts don't, in order to produce the right macro scale outcome? In other words, a pylon that has adjusted to that environmental pressure. Well, this is obvious and easy when all the forces are reversible. The stress on the top translates stress down to the members that are connected to the top, which translates stress down, and so on, in such a way that the ones which need to bend because they feel the stress of the pressure on the structure. Similarly, a mobile that's all balanced in equilibrium, if you add a weight or cut off a weight, the others all adjust in such a way to find equilibrium again, because the forces are translated through that system to the rest of the system in a way that tells it how to change in order to produce that outcome. So accommodation to stress or forcing is easy when you have reversibility. You just push it where you want it to go. You push on each part, and the response on each part is directed and specific. The bits that need to change, and they change in the right direction. Now, easy reversibility of this kind needs relationships that are smooth and monotonic and differentiable gradients with no discontinuities and no bifurcations, such that it's decomposable in independently additive components. Each of the little bits just add up to the whole in such a way that you can reverse it. There needs to be no hidden constraints or structure that stops that happening. But systems that have those smooth properties aren't programs. They aren't machines of the kind that we're interested in, the cognitive ones. Cognition requires those nonlinearities and discontinuities so that you can do logical reasoning, so that we can do conditional branching, so that we can hold hidden state. And systems like that aren't easily reversible. So this is the tension between the learnability of a system and the cognitive capabilities of a system. Learnability requires continuous spaces with gradients and directional error that can be reversed, but it's limited in the kinds of systems relations that it can learn in that way. Cognition needs a discontinuous space with hidden state and conditional branching that's capable of representing arbitrary complexity, but because it's representing arbitrary complexity, it won't be reversible. That seems to suggest an intrinsic opposition between things being reversible and things being cognitive. the kind of opposition that might make you think that if you want to create something really clever, then you're going to have to do it by trial and error instead of by following gradients in a continuous space. For example, if you were to try and write code in a high-level language, it's not possible to transform that code by pushing on it in such a way that you get the code that you want. Instead, you might resort to search. Maybe we could take a piece of source code and start modifying the ASCII characters at random and see whether it changes the code into what we want, but you're not going to get very far that way. Also, by the way, how do we explain how the code becomes interpreted into a cognitive machine in the first place, which is Perry Marshall's question. Now, it is possible to do learning in dynamical systems with recurrence, sometimes with limitations. And programmatic search in artificial neural networks is current state-of-the-art stuff. We're really looking for artificial neural networks which rewire themselves dynamically. It's the holy grail of topology search in artificial neural network territory, and there is ongoing work in that area. But suffice to say, this is the difficult territory in which we need to work. And it's the difficult territory in which AI is working. It's the difficult territory in which biology needs to work as well. Okay, so now I want to take that excursion into explaining how some of the aspects of how deep learning works into the elemental nature of deep learning. It's a bit technical and low level, but it's an important part of the story. We need to know about things like which functions are easily learnable, which ones are difficult to learn, and the concept of folding feature space to find hidden order or symmetry breaking that enables us to represent that hidden order, and the fact that that's recursive. We need these concepts in order to understand where we're going. So let's start with a shallow, easily reversible system to start with. A single perceptron represents a nonlinear output function, and the weights from the inputs A and B through that nonlinear function change whether the function is sloping upwards or sloping downwards, or the slope is over here or the slope is over there, but it's a single monotonic slope. That means that we can classify our two-dimensional input space into a one-dimensional classification of things which are in and things which are out for our one output function, one output variable. And that classification is going to be essentially, if we interpret it as a threshold instead of as continuous, a single decision boundary that separates one part of space, input space, from another part of input space. In this example, we have a decision boundary representing A and not B, so that that particular training sample, the plus sign is in the class and the others are out of the class, so the decision boundary correctly separates them. For a simple single layer perceptron like this, there's a perceptron algorithm that guarantees finding the weights that do the classification that you want for any linearly separable function of the inputs. How does it do that? Well, you take the difference between the output that you've got. You start with a random network. You take the difference between the output that produces and the output that you wanted for that particular input. And if it's not right, you take that error, the mismatch, and you use it to push backwards on the weights to change the weights in the direction that makes the error a little bit less. And then you put the next input in and you look at whether that's correct. And if it's not correct, you use the error to push backwards on the weights and bend them a little bit in the direction that makes the error a little bit less. As you do that over all of the inputs, the weights bend and give way in such a way that the decision boundary moves around until it doesn't need to move anymore, until there isn't any error. So you can see that the learning process for a shallow neural network is the same as just pushing an object into clay, right? We're just pushing backwards. The mismatch between the actual output and the desired output is pushed backwards into the structure of the system to bend it. And that's what the perceptron algorithm does. Now, if you have a pylon built with many layers, a deep network, you can still do that. It's still reversible. The backpropagation algorithm apportions change into the weights of the network in proportion to their contribution to the error. The one that was pushing the hardest in the wrong direction is the one that gets pushed back the hardest, the one that needs to deform the most. But that pushes on the nodes in the layer below, and they push on the nodes in the layer below, and so on. And that then pushes the structure backwards until you can get the output into the position that you want. Put differently, that backpropagation alleviates the internal stress between the components that's caused by the mismatch of the output with the environment. And you can use a deep network to collectively compute the same decision boundary that you could with a single layer perceptron. But now it begins to get interesting. What if there are two different environmental states that have the same observable, that they look the same in terms of what the output is supposed to be like, but they're really different contexts because there's a hidden or unobservable state in the world that you can't see. In other words, the output is one-dimensional, but it's being asked to model a two-dimensional relationship. This requires us to do induction, to infer a higher dimensional model from a low-dimensional feedback. So this is an example of a non-linearly separable function, XOR, where there are two training samples here and there, two which are in the class of the pluses and two which are not in the class. And it isn't possible to place one linear decision boundary in a position which separates the positives from the negatives, the ones which are in the class from the ones which are not in the class. That's why it's called a non-linearly separable function. You can't do that with a single layer perceptron, but you can do it with a multi-layer perceptron. And it's interesting what happens when you do. So when you present one of the training samples, and it turns out that it's classified it incorrectly, that causes the decision boundary to switch around. It's been pushed back in the other way. No, you got that wrong. It's this way around. And then you put another training sample in, and you said, no, you got that wrong. It's this way around. And then you put in another training sample, and you said, oh, no, you got this wrong. It's this way around. Because of that non-linearly separable nature, the decision boundary is going to bounce around, trying to find a way to fit there that doesn't require any further change, but there isn't a way to fit there that doesn't require any further change. And accordingly, the decision boundary oscillates around, trying to find a way to do both. And if you continue to push it in such a way, it splits. The decision boundary bifurcates such that the network now represents two decision boundaries instead of one. It can do that because it has the additional internal structure, multiple hidden nodes I've labeled H1 and H2. And one of those hidden nodes can do one of the boundaries and one of them can do the other. Here's a rather cool video that somebody created showing the bifurcation of data in the intertwined spirals function, pulling the blue dots and the yellow dots away in opposite directions. So that hidden node 1 can represent the decision boundary that takes care of one of the positive samples, and hidden node 2 can represent the decision boundary that takes care of the other positive sample. And then the output, the next layer, can combine those to put them together, or this positive one and that positive one together are both in the class. So in that way, those two decision boundaries together can be combined by the next layer in the network to represent the non-linearly separable function. Notice that those two decision boundaries, represented by H1 and H2, are the mirror of each other. One of them is B and not A, and the other one is A and not B. There's another way to solve it, which is not A and B, or not A and not B, the two decision boundaries that go this way instead of that way. But whatever decision boundaries you have, they will be the mirror of each other. They have to be the mirror of each other in order to represent this non-linearly separable function. And as they mirror each other, they are doing a symmetry breaking in the internal organization of the network. H1 is becoming the complement of H2. That internal symmetry breaking occurs, meaning that each interneuron, H1, hidden node 1 or hidden node 2, takes their meaning from the other. What do I mean by that? That there isn't a right answer for hidden node 1 that's determined by the input-output relationship. There's only a right answer for hidden node 1, that is, it needs to be the complement of hidden node 2. And there isn't a right answer for hidden node 2. It's just that it needs to be the complement of hidden node 1. That isn't determined by the input-output pressure. That's an internal symmetry breaking that occurs. Hidden node 1 can represent that boundary, or the one that hidden node 2 was doing, or this boundary, or that boundary. It can be any boundary that's sensitive to both of the inputs and still compute XOR correctly. And that's true for H2 as well. So there's no information from the external relationship to tell you what H1 should be at all. It's completely defined by its symmetry breaking with H2. Okay. Now, that symmetry breaking is folding the relationship between the inputs and the outputs, so that when B is low, the response from A is upward sloping, and when B is high, the response from A is downward sloping. So now the response is not monotonic. It has a fold in it. We can understand that fold as two apparently different regions in the input space are now the same region in the model space. That the input space is folded such that we have one concept that represents many instances, and one concept unfolds into many instances. One concept represents many instances, and two instances are folded into one concept. Sorry, I said that the wrong way around. That many-to-one and one-to-many relationship is what we mean by abstraction. I've abstracted this set of instances into one concept, the XOR concept, by folding the space. That many-to-one and one-to-many relationship is what it means to do learning, to abstract a set of instances into a high-level concept. And it requires induction to do that, meaning that precisely that the input-output relationship didn't tell you how to do it, that you are generating a general rule from data that didn't tell you specifically how to do that. So that folding over of the input space, which I can tell you is not easy to animate in PowerPoint, means that these 2 points are really the same point in concept space. Two different instances and the same concept are represented simultaneously in the same network. There's an undetermined relationship, therefore, that XOR represents both of those instances, which is that underdetermination is important for induction and for generalization. Okay, so can we still understand this as a kind of reverse engineering problem? Well, deep learning is still a transformative process, right? It's not variation and selection. It's a transformational process, not a search process. It's not so different from taking an impression that we're just pushing on a structure, but it's deep. It's deep meaning it creates an internal folding, that the stress between what it is and what it needs to be pushes on the internal organization of the network until it gives way and finds a way to resolve that stress by changing the internal organization, like a nut in a vise. That the desired relationship is pushing on the relation that's represented by the inputs-output relationship, and the actual relationship that the network represents is being deformed by the desired relationship. The resolution is an internal symmetry breaking, an internal reorganization that moves into an additional degree of freedom. Now, that moving into a new degree of freedom is just pushing on something, right? When you push on the top of the strut, you apply a vertical force, the strut pushes back. But if you push harder, it gives way. It pops out into an orthogonal dimension. The symmetry is broken to accommodate the stress on the steel or whatever it's made of. Notice that there are two ways to pop out in that orthogonal dimension, like the two ways of solving XOR. That which one you get is not prescribed by the forcing. It's necessarily in an orthogonal dimension. Interestingly, girders will bend in different ways with different numbers of curves, depending on the constraints which are placed upon them. And also interesting, when you push on a girder that has any internal integrity, it creates a rotation inside the girder because the inside of the curve is under compression and the outside is under tension. And to resolve that, it tries to turn around to producing twist in it in order to resolve the tension that's created internally by the tension that was created in the length. Very interesting. Don't really need that right now. The forcing from the outside underdetermines the internal structure. That's what it means to be a deep learning process rather than shallow. And that requires induction, meaning that the forcing doesn't specify how to move in that additional dimension. The internal dimensions are determined by internal symmetry breaking. Now, we usually think that the trainer is imposing structure on the learner, and the learner yields to the pressure. But the learner is acting on the world too. Like when you ask the learner what's the actual output, it's giving answers back to the world, and that's what you can push back on. But in the pushing outwards, it pushes back on the environment. Learning systems are active, not passive, or at least real ones are, unlike artificial neural networks. It's a symmetric relationship that the environment changes the organism, but the organism changes the environment. It pushes back on the environment. And that two-way relationship keeps changing until the stress is alleviated, until there's no more force of change, either because the organism has changed the environment or the environment has changed the organism. If we think about that as one piece of clay pushing onto another piece of clay, both of them accommodate in such a way that they find equilibrium. Now, if we were talking about dynamical systems instead of passive shapes, it would be a dynamic equilibrium where this thing acts in the world in response to its inputs, and this thing acts in the world in response to its inputs in such a way that they now don't need to change anymore because they're not surprised by the inputs that they get, in the language of Friston. So that two-directional or bidirectional relationship, it comes from the two systems, the environment and the agent, being pushed together to resolve their differences. And instead of pushing straight back, it causes an internal symmetry breaking that pushes into another dimension where their differences can coexist. The inputs to one are the outputs of the other, and the relationship in the environment is mirrored by the relationship in the organism, and vice versa. But this isn't just about data structures or information. This is about processes of construction. The construction process of the organism and the accommodation process of the environment push back on one another in a way which mirrors one another. Not just passive information or static geometric concept. It's a mutual co-construction of one another. And they need to be the same as one another because they define one another. There isn't any right way for the organism to be or any right way for the environment to be, except in so much that it mirrors the other. They must be the opposite to one another. In the same way that the internal symmetry is broken between the two nodes of the network in deep learning, as the learning process is causing that internal symmetry breaking, it's also a mirror of the relationships that were out there in the world. The world was presenting an XOR function that it needed to learn. The world was an XOR function. And if that can't change, then the learning system has to give way and become an XOR function. But if they were both dynamic, then they do a symmetry breaking, where if you're going to be an XOR function, I'm going to be an XOR function. If you're going to be if and only if, I'll be if and only if. If you're going to be a linear function, I'll be a linear function. There's a symmetry breaking between the organism environment that's exactly the same as the symmetry breaking between the nodes within the network. The two processes are mirroring each other. Who's doing the deforming? Who's the teacher and who's the learner? Is it A or is it B? It's symmetric. They're under stress to symmetry break, and they need to mirror each other to be the same but the opposite of each other. Who's pushing them together? Who's pushing the organism into the environment? If the environment isn't a learner that's pushing on the organism, and the organism is just as much pushing back on the learner, why were those two things being pushed together? You see that it's recursive? When we thought about the organism being pushed on by the environment, we said, these two nodes are being squished together and they pop out into another dimension because the learner is forcing them. But if the organism and the environment are also in a similar kind of relationship, they're being pushed together and caused to pop out to differentiate organism from environment. Who's pushing them together? Can they push back on that? Meta, meta, meta. It's going to get fun. In biological systems, changes to deep structure don't break all the details. The details accommodate and adjust autonomously. Each level of organization knows what to do, even for situations that they haven't seen before. Those are some of the examples I was talking about in the introduction. And that's true across huge physical scales and temporal scales, evolution, development, behavior, and physiology. How does biology do that deep changes to structure that accommodate and adjust autonomously at multiple different levels? Well, if we think about it as a recursive reverse engineering process, then macro-scale stress causes big changes to the internal structure of a system in a coarse-grained sort of way, like, this is going to move around that, and that's going to move around this. But those big changes are going to create stresses at the next level down, that this organ is not usually in that position, this limb is not usually over there. And that creates stresses at the next level down. So now all the blood vessels and nerves need to accommodate to those changes, which results in smaller changes to their internal structure, and so on and so on and so on, which creates stress down at the microscale, which result in innumerable changes to the small scale structure. Now the gene expression of this cell in this blood vessel, in this organ, in this limb needs to be different because of the macro scale changes. So the macro scale stresses are pushed down to the micro scale changes. Each grain is doing, at each level, is doing its own symmetry breaking, its own stress accommodation, and passing on the remainder to the lower levels for them to respond to. Each level's response is not determined by the top, it's underdetermined, but it is top down, not bottom up. Does it always work? Well, when it fails, it's because you have a catastrophic failure, a fold which doesn't keep its bounce. Each level needs to be a shallow change. Like, you can do induction of an XOR function, but when you do induction of a really deep function just by pushing on the outside, you get a catastrophic failure. Each fold needs to be subtle, to not go beyond its breaking point and fold right over, so that it stays reversible and elastic and you don't get a catastrophic failure. And thus, it continues to push back. It's still able to push back, that the little components maintain their internal integrity, such that if the pressure at the macro scale is released, the internal components can push back or spring back. They know how to unfold to be their natural self rather than their stressed or compressed self. Catastrophic folds make inert information at best. Catastrophic folds make material inert. They make it unable to push back. It's kind of like origami, where you just fold things over and fold it over and fold it over and fold it over, and you've got something with the shape of a crane, but it's not actually a crane. I think that deep artificial neural networks are a bit like origami figures. They're folds on folds on folds that compress the feature space, as they must in order to learn non-linearly separable functions. But I think they do it catastrophically in a way that can't spring back, and they lose their agility. Regularization is a pressure that tries to keep things simple so that they sort of spring back. But this is a springing back that only happens on learning timescales. It doesn't happen dynamically in the behavior of the system. It's just a sort of a compromise way of doing it. The trouble is that you can't really control or reverse deep folds if you're just pushing on the top level. If you're pushing on the top level, the piece of paper just crumples up. Now it's all folded up, and you can make it fold in the way that you want, but you broke it, right? You did catastrophic folds. It's become inert. You collapse the concept space. And in an artificial neural network, it isn't totally irreversible. You can train a network for one thing and then train it for another thing, but it becomes even more difficult to train after you've trained it for something else. What are you going to do to make your second origami figure after you've made the crane? Are you just going to flatten the crane, treat it like a funny shaped piece of paper, and then start folding it into something else? Or you could unfold it all back to a flat piece of paper and then start again. But both of those require you to undo all of the work that you did or ignore all of the work that you did in the first structure. You don't have the internal dynamics that gives you the kind of agility that you see in biological systems. It's a bit like we can push clay into the shape and form of an object that we want, but after we've made it with all of the exquisite detail, now what if we change our mind about something at the macro scale? What if we want to turn the head to face over the shoulder? He says, pushing his hands that way and turning his head that way. We want to turn the face around. How could we do that? It's like, well, if we just push it, we could get the head to turn, but in so doing, we'll obliterate all of the fine features on the face. Another option would be, well, we could do lots of tiny little pushes, tiny pushes, tiny pushes, tiny pushes, tiny pushes, tiny pushes, so that the head turns and maintains the integrity of the details as we turn. But that takes an exponential number of little pushes, the same number of little pushes as it took to make the face in the first place. What you really want is to be able to push on it, and all of the fine scale features take care of themselves. Not just as the head turn and the features go with it, but the shoulder girdle begins to move because the neck has changed. And if you push it further, then maybe they step back to stop themselves falling over, or sit down, or push back on you, or run away. In other words, we want the system to be autonomous in a deep way and not just a superficial model, even if it does have a lot of detail. If you can't really do deep folds in a controlled and reversible way by pushing on the top level because of the massive underdetermination of the internal structure, maybe they can do it for themselves. This would mean that you're not doing a fold on a fold on a fold on a fold that makes an inert structure in a fixed space, but you're doing a folding process that's acting on a folding process in another dimension, that's acting on a folding process in another dimension, so that the top level isn't trying to do all of the work. What would that be like? It's like a process that opens up new dimensions within dimensions within dimensions when needed, a radically fluid space of possibilities. Notice that the weights in each layer of an artificial neural network are not really meta weights. The bottom layer of weights tells you how to organize the input states, the input features, but the next layer doesn't tell you how to organize the weights of the first layer. It just does another fold on top of the outputs of the first layer. If the first layer did correlations between the features and the second layer did correlations between the weights, that would make the first layer dynamic. Then you would have a dynamic, metadynamical topology of your system. That's the kind of recursive process that we need, rather than just a folded structure. How the hell would you design that? Answer, you don't. Because design is a concept that pretends to be able to see the whole thing, to see all of the layers, all the way down to the microscopic. I'm going to put all of the parts in the right places. You can't do that. Each layer needs to organize the layer below in an underdetermined way, and the symmetry breaking that the lower layer does is not determined by the higher layers. The upper layer can't see through to the other layers. They have to sort of trust that they will sort it all out amongst themselves. But the lower layers also have to push upwards because they determine the points of articulation that are possible at the top layer. You can't just, I'm going to turn half the head this way and half the head that way and expect the skull and the brains and the blood vessels and tissues to sort it out, right? The kinds of articulation which are possible at the top level are also determined by the pushing back of the lower levels. They determine the movements which are possible at the upper levels, so that when the system is stressed, all the levels are involved. The top level reorganization is pushing downwards on internal structures, is pushing downwards on internal structures, is pushing downwards on internal structures. But the bottom level is also pushing up and telling you what kind of movements are possible at the upper level. You can see that that happens automatically in the pylon, right? When I push at the top of the pylon, the stresses go all the way back down to the members, and the way in which they give way and the stresses which they feel are partly determined by how hard the other members are pushing back. If this bit was rigid, it would just buckle. But if that bit is flexible, then the stress is transferred downwards through the levels. It has more agility. In other words, it needs to be engaged, top down and bottom up simultaneously for this to work. How could that be possible? You have to be able to fold the space right over in order to make two instances into one concept. And as you do that, you necessarily lose control of the deeper underdetermined dimensions. And that only gets worse as you push deeper. How could it be possible that the top level can reach the deeper levels, even if it's only in a broadcast sense? how can the deepest levels push back up to the top to make a difference to the space of possibilities all the way up there? How can the genes be pushing back on the physiology of an organism to say what kind of physiological changes are possible? But if they don't have that connection, then the top will create stresses that the lower levels won't be able to respond to. That's catastrophic failure. And the pushback at the lower levels will meet immovable objects at the upper levels and a loss of upward control. Is it possible to have all of the levels really engaged with the transformation process that needs to happen simultaneously, the whole stack engaged upwards and downwards? That's the problem of biology in mind. Recursive, reversible, inductive engineering. How can you naturally and easily induce deep causal structure, like programs, from experience and contact with the world spontaneously, by which I mean you just get pushed that way, in such a way that subsequent change, reprogramming, deep program adjustment remains easy? That contact with the world can change deep structure and all the details aren't broken, but they accommodate and adjust autonomously. All the details know what to do, even for situations they've never been in before. So instead of thinking about a recursive data structure with folds on folds on folds on folds, but it's passive that needs an interpreter in order to read what it means, like there are differences all the way down, we need to think of it more as a transformational process all the way down that pushes on the next level down, that pushes on the next level down, and that pushes back up. Here it comes back up to the next level, up to the next level, up to the next level, up. Yay. I'm really pleased with that animation in PowerPoint. Not just in a ebb and flow, but in simultaneously pushing upwards and pushing downwards at the same time. That's the real problem of living systems and cognitive systems. To finish the introduction, I want to talk about Desiderata, a list of desirable things for a new theoretical framework, in particular for a physics of cognition. Some of these ideas I've introduced already when I was talking about what the real problem was, so there's a lot of them, but it will go reasonably quickly, I think. So number one, we want to be able to do direct induction. We need a suitably impressionable substrate such that experience or contact with the world causes an imprint, a deformation that naturally constitutes an impression of what happened, of that interaction with the world. In other words, it creates a memory. Memory should happen by direct induction by the environment, so that stress between the subject and the environment causes memory, learning, problem-solving competence spontaneously when it's in a suitably impressionable substrate without needing to do search. In other words, it's a transformational theory. But it needs to be deep, not just a shallow or first-order imprint like your hand in clay, just the superficial appearance, not just a three-dimensional structure, but a deep structural model with internal organization that's induced by contact with the environment. And because it's doing induction, that means time has to be involved because you can't see all of it in one go. You have to make many observations over time in order to put that structure in order to be able to induce the hidden state. Then we'll have an impression that's not just a static structure, but it has dynamics. Its internal causal architecture models the outside world. We need to be able to do induction of a deep causal model easily. We also need it to be the case that it solves the mind-body problem, that it's embodied, embedded, and empowered, that when X models Y, X is not just a representation or a surface structure model or a movie of Y that has the same appearance, but that X has the same sensitivities to the world as Y, and X produces the same effects on the world as Y. I'm going to call that embedded and empowered. And that seems a little bit fantastical. You might call it a sort of causal impersonation, not just an impersonation, but an impersonation that has the same causes, the same effects in the world, so that the model does the work without an interpretation machinery or interpreter, so that we don't have a mind-body problem. Think about Newton's cradle, right? You lift up a weight on one end and you drop it, and it makes the weight on the other end come up. It is, in a sense, a model of what happened over here that happens over here, but it's a mirror of it, but it has the same causal efficacy. That model pushes back on this ball and it comes out the other end. the Barton's pendulum, you have a bunch of pendulums of different lengths and one driving pendulum, and you swing the driving pendulum and it picks out the resonance through the string, picks out one particular pendulum that resonates to the driving pendulum. But that pendulum is itself a pendulum. It has the ability to drive other pendula if there were other pendula of the same length. It is also pushing back on the first pendulum. That's what happens when you put two metronomes on a wobbly board. One of them is producing a little vibration in the board, and it's causing the other one to entrain to it, to resonate with it in phase. But it's also pushing back. They are mutually co-defining one another. They're modeling each other. This needs to be substrate independent. The causal impersonation can be made out of different stuff, but work the same if they're suitably impressionable. So we could have a pendulum that keeps time, or a rotary timekeeping device, or the drip of water, or an electrical circuit with a vibrating crystal in it. And the coupling between those different substrates should work the same, that they can do causal impersonation of one another, even though they're made out of different stuff. So it doesn't really matter that the ball on one end of the Newton's cradle is made out of steel. It's only matters that it's capable of taking the same impulse and holding it for a moment and then delivering it back. So if the two systems are weakly coupled, the balls on the Newton's pendulum are arguably strongly coupled. If the two systems are weakly coupled, then they can induce or resonate with one another between those different substrates. It should also be scale invariant, that you can do a causal impersonation and make a little really, really tiny model of things, or make a huge model of things, or vice versa. If they're suitably impressionable, it should be scale blind, that any scale can talk to any other scale. A way to understand how this might work is coupling across scales, is that when you have a metronome of one twice the frequency of another, which I've depicted as a small metronome, but it isn't really, is a shorter pendulum, that will also phase lock with one another to produce a phase locking where one is beating twice for every one beat that the other one does. And it doesn't really matter whether that fast frequency metronome is made out of another metronome, or whether it's made out of, I don't know, a gene regulation network or something. So long as there's some coupling between them, it doesn't matter that one is tiny and one is large, and one's in one substrate and one's in another substrate, because they're in different substrates. They can be different sizes. If they resonate with one another, then they can still do that kind of causal coupling. Oh, here's a little story about how this might be relevant to the deer antlers. If you could move a vibration between substrates, I don't know if I'm ready for this story yet. I'm going to come back to it later. I'm just going to say for now, I'll come back to later about how this might help us understand what's going on with the deer antlers. Also, moving into the sort of cognitive realm rather than physical realm, it should be able to do abstraction. Do you have a many-to-one and a one-to-many relationship to represent general classes and specific instances at the same time? That many instances fold into one concept, a sort of compression, and unfold back into many instances. If you imagine the pendulums again, you have one driving pendulum, and maybe there were four other pendulums that were all the same length as that, and they would all resonate to that one heavy weight. Conversely, if you got all four of them swinging, even though they're light, they could get the larger mass pendulum to be the response, many-to-one, one-to-many. That works both ways. But the relationship shouldn't be one-to-one. There should be an underdetermination, that there are various small instances that fold into one large concept, into the constrained space. You induce a general class, and one large concept unfolds into various small instances that's deconstraining into various variants or specific instances. David Bohm, quantum mechanics, talks about implicate order and explicate order, that there's a folding of space that takes all of the symmetries, and there's an unfolding of space that has all of the differences. And in all the way that those differences fold up in order to make that one implicate order, and physics is happening in both of those spaces at the same time, but one of them is underdetermined by the other. And to make this more mundane, to put it into a sort of physical realm, if we had a many-to-one relationship, but we also had that change in the length, the resonant harmonic between the pendulum with twice the length and the pendulum with half the length, like the big metronome and the small metronome that lock harmonically, then there's a phase underdetermination between the swing of one is two swings of the other, so they can be locked two different ways onto that phase locking that occurs. That's a clue about where we're heading. This will mean that the impression that it's taking is doing induction because of that underdetermination. Now, movements in the implicate order need to create movements in the explicate order. Multiple points in the high-dimensional unfolded explicate order correspond to a single point in the lower order folded space, the implicate order. But entities experience causes in both those spaces simultaneously. That if I alter the small pendulum, one of the small pendulum, or many small pendulum, or I alter the big pendulum, they are coupled with each other. The forces are moving back and forth between those two things. I'm not just pushing on one and the other is reacting. I'm not just pushing on this one and the other is reacting. I'm pushing on both of them when I touch them. Entities experience causes in both spaces simultaneously. In either one space, movements look ordinary. They look like the single order optimization process. If you just look at the big pendulum, it's just swinging. If you just look at the little pendulum, it's just swinging. But when you put them together, you have pendulums that appear to do something weird. This pendulum appears to be making itself swing. It's speeding up rather than slowing down, and it's swinging itself. Of course, it's not really swinging itself. It's because it's picked up, it has an energy which is coupled to the larger pendulum, which is driving it through the resonant vibrations. So my conjecture is that agential behavior, a behavior that looks agential in the folded space, is a projection of ordinary behavior in the unfolded space, is a projection of ordinary behavior in the folded space. It's a bit like saying that to the well-informed chess master, the next move is obvious. It's a forced move. There isn't any search required. It's just like, well, you have to do that. And that looks magical to the uninformed, but in the conditioned mental representation of the master, it's just a least action thing. It's just falling downhill for the chess master. It's all obvious. That makes things look like they're doing spooky things within a motive, like pendulums that speed up. But really, it's just a straight line in a curved space. This is artificial potential fields as a way of organizing agent behavior to move around obstacles. If you had a model of a potential field around the obstacle that pushed you away, and you do a least action path in that space, you go around the obstacle as though you could see it coming before you bumped into it. Now, this is something that we sometimes talk about in the context of evolution by natural selection. We talk about what's the prime directive, what's the meaningful direction to it all, because the meaningful direction for life seems to be different from the meaningful direction to physics. Physics seems to be on a unstoppable trajectory towards an increase in entropy. But living systems, at least locally, go the other way, creating order. Natural selection suggests a directionality of trying to increase survival and reproduction. I've heard people say to maximize inclusive fitness, if that floats your boat. But if there's a different prime mover, if it isn't selection that's doing it, what is the direction of that prime mover? Like if the direction was exactly the same, it wouldn't really matter. We would just be describing the same thing. Different words for describing the same process. But if they're not the same, then that's not what it's doing. It's not trying to increase survival and reproduction or maximize inclusive fitness. It's doing something else. What else? What is it optimizing? If we really understood what was happening, we ought to be able to answer that question, such that some movements in this space are better than others. Why do you need some movements to be better than others? Why can't you just say that's what it does? Because otherwise, if you don't say that, you're just saying stuff happens. You don't want to just say stuff happens. You want to say we want to understand it as in a goal-directed way. There isn't any intelligent action without goals. Otherwise, it's just different attractors. There isn't any adaptation without value. Otherwise, it's just different frequencies of stuff. So we need to understand what that prime mover is. So examples or possibilities of prime movers that people have talked about, right? So there's the what persists exists prime mover that just, if you don't change anymore, then you will carry on like that. And if you do change, then you won't be like that. So the things that you see are the things that don't change. This leads to refinements of stability and robustness, or ultra stability from Ashby. There's the moving towards order, or order for free, or self-organization. But we don't just want order. We want things to be adaptive. Well, there's adaptation, the idea that things are improving at what? At survival and reproduction. What would it mean if it wasn't about survival and reproduction? They're getting better at problem solving, better at resolving conflict or frustration, maybe. Or is it actually about a creative process? Because what problem are they solving? Are they still solving the survival and reproduction process, or is it something else? I'm going to suggest a movement that moves away from what persists exists, which has a sort of a static, sort of like you already had everything that was interesting and you're just picking out the ones you want to keep and the others that you're going to discard, but towards something which is a prime mover, which is fundamentally creative. That's almost polar opposite of what persists exists. We're in the territory, therefore, of talking about things like affect, what is it like, of value, which way is improvement, aim, what is it trying to do? And there's an issue here of what are you doing? Are you just taking an intentional stance because it's convenient? Or are we really doing an affect first way of understanding things? So I'm going to come back to this at the end, because it's related to the question of what does it all mean? And it's important that we talk about that, because otherwise we don't really have an intuitive understanding of how to interpret all of those details. Number 10, it should deal with recursive linguistic competence. The matter should be agential. It should be enzymatic as well as informational. We talk about this in the terms of the RNA world, right? That the RNA is informational, but it's also enzymatic. It also does stuff. So matter, the kind of matter that we're talking about, should be both. It should be information and it should do stuff. That the concepts do the work of what they mean. They execute their own function. They have causal power. They're not inert information that needs to be separate, that needs a separate interpreter or executive to read the information and then do it. They do it for themselves. Concepts should be zoomable, a sort of natural hierarchical ontology, the class-instance relationship, that we can manipulate them as abstract idealized types, or we can manipulate them as particular instances that are grounded in the specifics. Well, these are like a language that does stuff, right? We want a linguistic competence where we have productivity, that we can create an infinite number of possible utterances, compositionality, that the meaning of a system comes from the meaning of the parts that it contains plus their organization, that it has systematicity, that if you can understand the relationship between A and B, you can understand the relationship between B and A, and that it's recursive, that creates grammatical structures or sentences, plus some sort of very simple operator like merge that tells you how two sentences interact with one another, but not like we're manipulating passive data structures, but that they do it to each other, almost like it's a chemistry, a linguistic chemistry, a language with causal power, with the words that do stuff, that make stuff in sentences that learn, that aren't static, that in interacting with one another, they get transformed and they do error correction. By being spoken, they self-correct themselves. Properties like that. Also, we need our theory to explain biology as we know it, or at least as we think we know it. We need it to explain how it organizes physical bodies and explains development. It explains how genetic encoding works, why genes sometimes at least control phenotypes, and why they often don't. But development and reproduction still works. We need to know how to read physical bodies and write them downwards to downward causation. That resolves or explains the genetic correlation between genotypes and phenotypes. We need to explain how it adapts over time. In other words, we need to explain biological evolution. It needs to be compatible with that, so that it explains how structures can be self-reproducing to write from one subject to another, and we can transfer the agential action or the self from one body to another, and explains, in other words, biological evolution, how it's so amazingly clever, and how that does have something to do with natural cognition. And finally, the 12th item on our list of desirable features is that it all arises spontaneously from nothing, with no designer, no programmer, no special machinery. It all arises, well, not from nothing. It arises from physics, from maths and geometry, from the interplay of space and time. I don't know, something pretty simple. Here's our list of 12. Direct induction from a suitably impressionable substrate that's deep, so that it has the same causal architecture, not just the same surface structure. That's not just a movie, but it's embedded and empowered. It has the same causal power in the world. That's substrate independent. You can implement it in anything. It's scale invariant. You can do it at any scale. It handles abstraction. You can go from many instances to one concept. That you can do induction because the relationships are underdetermined. That many instances which are different from one another correspond to one concept, and one concept unfolds into many different instances. That you get agential movements from ordinary movements in the implicate order that looks like they're clever, but really they're ordinary if you understand the space it's moving in. It has a prime directive that makes sense to us, a meaningful direction to life. It's recursive linguistic competence that's actually agential. It explains biology as we think we know it, and it arises spontaneously from nothing. That's what's needed to solve the deep recursive reverse engineering problem. And that's the conclusion to the introduction.